So when we start mixing acids and bases together, we're going to call this a titration. And so generally what we'll do is we'll add something strong to something weak. And so in that case, we're going to think about the molecules fighting with each other to neutralize. And this is going to completely go to products. It's not going to be equilibrium. So we'll think about the molecules fighting, and we'll use an ICF table. And so when you use the ICF table, we'll end up plugging in moles and treating it like a limiting reagent problem. And so we'll go ahead and we'll do our ICF table, see what is left over after the limiting reagent is consumed, and then figure out how to go about our next step from there. And so let's just quickly look over again how to determine whether something is an acid or a base. So acids are oftentimes written with an H out in front. We see this with all of our strong acids and then some weak ones also. Or we look for carboxylic acids, and these have the COOH group written at the end. Or if you have something that's given a Ka, it's a pretty good sign that's going to be an acid. Okay. And then we have our Lewis acids, and these are small positively charged species like iron and aluminum and maybe silver. And these are molecules or atoms that can accept electron density from something like water, which will then dissociate to put a proton in solution. And here, if we have a nitrogen, a hydrogen, and a positive charge, that will be acidic because those molecules can donate an H+ and reform the neutral basic species. For identifying bases, we'll have most metal hydroxides, like the strong bases that we've talked about. Or we'll have ammonia and amines. So this is a nitrogen with a lone pair on it. And then if you have a Kb, that's a good sign that the molecule they've given you is a base. And then if we have the conjugate of a weak acid, which will normally carry a negative charge, then those can be bases. And there are other videos that help categorize and learn how to categorize acids and bases. And so if you feel like you're concerned about this part, go back and check those out. So let's go ahead and look at this problem. We're going to figure out the pH of that buffer solution that we made before after we add 0 or 10 milliliters of 0.1 molar HI. And so HI, we know, is a strong acid. And so we have to think about how to write the reaction, and we have 3 molecules that are around. So I go ahead and I always start with whatever the strong species is and let that be in charge. And I'm going to write it just as H+, because the iodide's going to be a spectator. And so now I have to figure out, well, which of the other 2 molecules is the H+ going to want to react with? Is it going to react with my acetic acid, or is it going to react with my potassium acetate? Or we can just think of it without the potassium and the acetate ion. So H+, strong base, strong acid, so it's going to want to react with base. So it's going to react with the CH3COO-. And our product is going to be then the acetic acid. Okay, and this is not an equilibrium, right? they're going to completely go to make products in a neutralization reaction. And so we're going to use an ICF table. And we're going to use moles in our ICF table. So again, we'll use the relationship that moles is equal to liters times molarity to fill out our ICF table. So we'll have 0.01 liters of 0.1 molar H+. We'll have 0.001 moles of H+. 0.03 moles of acetate, and 0.02 moles of our acetic acid. And so now for our change, we're just going to look at what the limiting reagent is. So we'll look at our reactants and see which one we have fewer moles of. And that's going to be the H+. So for our change, we'll use up all of that until we have none left. And we'll use that up from the acetate also. So we'll end up with 0.029 moles of the acetate. And when those react, they're going to form our acetic acid. And so we'll have 0.021 moles of that after the reaction. And so we have conjugate base and weak acid. So we still have a buffer, and we can plug into the Henderson-Hasselbalch equation using those amounts. So we'll have pH is equal to pKa, which is going to be the negative log of the 1.75 times 10 to the minus 5 plus the log of our base, which is going to be the acetate, divided by the amount of our acid, which is acetic acid. And we end up with a pH of 4.897. So if you compare this pH to the problem we did earlier, you can see that the pHs are still really similar. This pH is a little bit lower, but still really similar to what we calculated before. And that's because this is a buffer. It's going to resist changes in pH. And so us adding in strong acid didn't really move us that far away from our starting point. Okay, and so now we have kind of like the boss fight of acid-base chemistry problems. These ones use all of the skills we've used so far to figure out what the pH is at the equivalence point when titrating something weak with something strong. So here we have a titrant, our analyte is this weak acid HNT. It's made of acid. It's using our favorite element of titanium. We have a Ka of 4.09 times 10 to the negative 6. And we're going to titrate that with lithium hydroxide. So sometimes it does help to have a little picture of what's going on. And so we can think, we have our beaker, and it's starting with 500 milliliters of our HNT. And we're going to have a burette, and from which we'll add our lithium hydroxide. And we're going to do this until we reach the equivalence point, which just means we're going to have equal moles of acid and base. And so before we even really start the problem, we can make a prediction about what our pH is going to be at the equivalence point. So we have a weak acid and a strong base. So as we react our weak acid, we'll start making conjugate base. So at the equivalence point, we'll end up having water and conjugate base. So our pH at the equivalence point is going to end up being greater than 7. Also, you can kind of think if I have something strong and I have something weak, the strong thing is going to determine what my pH is at the equivalence point. And so since we have a strong base, our pH is going to be a little basic at the equivalence point. Okay, so let's go ahead and write our reaction. When I have something strong in solution, I like to start with that and let that dictate what I write. And so I'm going to start with hydroxide, disregarding the lithium because it's a spectator. I'm going to add that then to my lithium to my HNT. And this is a neutralization reaction. It's going to completely react and totally go to products. And those products will be water and NT minus. So we have a neutralization reaction. We're mixing acid and base together. And so we're going to use an ICF table. And we're going to have to use moles. And so they told me I have 500 mils of 0.3 molar HNT. So I'll end up having 1.5 moles of HNT. So they don't give me a volume of lithium hydroxide. They just give me the concentration. And so at this point, I'm going to go ahead and say for equivalence point, I'm going to add equal moles. I'm going to have to add as much volume as it takes so that I end up with 1.5 moles of hydroxide added in. And so we're going to have to figure out what that volume is. And so we know we needed to add 1.5 moles, which is equal to some amount of liters, times our 0.5 molar solution. And so we would have had to add 300 milliliters of our lithium hydroxide to reach equivalence. And so then once we do this now, our final overall value is 800 milliliters. Okay, so as we continue to work through this, I'm going to disregard the water, and we'll have 0 moles of the NT minus to begin. And since these are both limiting now, we'll use up both of them and have neither of those left over. And we'll make our NT minus. So now all we're left with is conjugate base. And so we know this is a weak base. And so if we put a weak base in water, we'll end up with a base hydrolysis reaction. And we'll be left with hydroxide. And so now we have a weak dissociation. We're going to be at equilibrium, and so we're going to have to use an ice table to solve this. So let's go ahead and kind of start fresh. Okay, so after we reacted our weak acid and strong base to equivalence, we're left with 1.5 moles of NT minus in 0.8 liters of solution, or 800 mils of solution. And we know that that conjugate base will do a weak base hydrolysis, for which I've written the reaction here. And since this is a base reaction, we know the equilibrium constant we'll need is a Kb. And so we're at equilibrium, so we'll need to use an ice table. And whenever you use an ice table, we need molarity. And so to get molarity, we'll just go ahead and say moles per liter. So our concentration of NT minus will be that 1.5 moles divided by our 0.8 liters. So our molarity of NT minus is 1.875 molar. So that's what we'll go ahead and put in for our initial amount. Disregard water as a liquid. We'll have neither of those to begin. So our change here will be minus x. And then we'll add x to both of these sides. So at this point, we want to set our equilibrium row to our equilibrium expression and use our Kb to solve. We have a problem though, and that the description of this problem gave us a Ka for the HNT. So what we're going to have to do is use Kw to figure out what our Kb for the conjugate base is instead of having the Ka for the weak acid. So we know Kw is equal to Ka times Kb. So Kb will be equal to 1 times 10 to the minus 14 divided by 4.09 times 10 to the minus 6, giving us a Kb of 2.44 times 10 to the negative 9th. And so now we can use this number to solve for x. So we'll have x squared divided by 1.875 minus x is equal to 2.44 times 10 to the negative 9th. And that exponent is definitely small enough that we can go ahead and ignore added and subtracted x's. And so to solve this, we'll just multiply over by 1.875, take the square root, and solve for x. So x equals 6.77 times 10 to the minus 5 molar. And from my ice table, I know that x is equal to the concentration of hydroxide. So when I go ahead and take the negative log of this number, what I'll end up getting is POH. And that number is 4.16. And so now to get pH, I'm going to do 14 minus 4.16 and get a pH of 9.84 at the equivalence point. And if we look back at our prediction, we said it should be greater than 7 at the equivalence point, and our pH indeed is, and so this answer makes sense. Okay, you guys are doing great. Hang in there, keep practicing, you'll start seeing the patterns, and just keep working like you have been. And be sure to take care of your minds and bodies as you go through and do this. Okay, talk to you later.